Our last lesson in Chapter 2 is 2.8, Graphing Linear Inequalities in Two Variables. Just as a little bit of review, it says solve negative 3x is greater than or equal to 15 and graph the solution on the number line. If we start with the inequality, negative 3x is greater than or equal to 15, to get x by itself, we're simply going to divide both sides by negative 3. Recognizing that when you divide by a negative, the sign switches, so it turns our inequality in the opposite direction, and 15 divided by negative 3 is negative 5. Notice this is a one inequality solution. This isn't an absolute value inequality. Therefore, when we sketch our solution on a number line, we're just going to have one arrow. So remember, we want to recognize the location for 0. I'm just going to count a couple to the right, a couple to the left. I'll go 2 here, negative 2, negative 4, over to negative 6. If x is less than or equal to negative 5, we'll put a boundary with a closed dot, and our arrow goes to the left. This is graphing with one variable in one dimension. On the back, we're going to look at graphing in two variables using a coordinate system. Technically, there are 4 different types for the parent function. We can have y is less than x, y is greater than x, y is less than or equal to x, or y is greater than or equal to x. Our goal is going to be to recognize how to kind of differentiate the number line versus a coordinate system. Now, as you look down below, I've got quite a bit to write here. Graphing linear inequalities. The first thing you want to do is get y by itself if necessary, and then look at the type of inequality you have. If you have just a greater than or just a less than, your inequality is represented by a dashed boundary line. If it includes the equal bar underneath, then your line is a solid line for your boundary. Then look at direction. If your arrow is less than or equal to, you want to shade below that line. If your inequality is greater than or equal to, you can shade above. Now, sometimes this gets tricky. So here's a little tip to always be able to tell where the direction is or where the shading should go. If you test a point like 0, 0, and your answer is true for the inequality, that's the side of the line where you shade, where that point would be. If your answer is false, then you'd shade on the other side of the line. Pretty common, it's easy to use 0, 0 unless that's actually on the line itself. All right, make sure to get all that written down, and then let's look at some examples on the right. Let's start by graphing one of the 4 parent functions. Y is less than x. Thinking about slope-intercept form, this means y is less than 1x plus 0. So if I think about my y-intercept of 0, 0, my slope goes up 1 over 1, up 1 over 1, all the way to the top, and down 1, 1 to the left, to the bottom. You're going to want to draw your inequality boundary from edge to edge. Since it's a less than, this is going to be a dashed boundary. So connect your dots with just kind of dashed segments all the way through, like so. And make sure on your paper that that's clear. Also, because it's less than, we're going to shade below. And shading below just means wherever you see it cross the y-axis, anything below that would be the side you shade. So we can use all this shading over here on the right. Let's look at some other examples down below where our slope and y-intercept are different. We're asked to graph the following linear inequalities and shade the appropriate half plane. The appropriate half plane is just like the shaded solution, because technically your graph goes beyond the picture that's given. We have y is less than or equal to 2x minus 1. Starting with our y-intercept of negative 1, the slope is 2 or 2 over 1. From our y-intercept, I'm going to count up 2 and go 1 to the right, count up 2, go 1 to the right, and again all the way up to the edge. And then if you go in the opposite direction from your y-intercept, down 2, 1 to the left, down 2, 1 to the left. Noticing that our inequality is less than or equal to, this is going to be a solid boundary line, just like we were sketching an equation. So go ahead and connect those dots with a solid boundary, edge to edge. And again, less than or equal to, we're going to want to shade below. So if you go where it crosses the y-axis, values that are below would be down here, meaning everything on this right-hand side needs to be shaded. But here's my other tip. Remember I said you could always try checking a value, like plugging in 0, 0. So if you ever want to check to see what side to shade on, if you plug in 0 for y and 0 for x, I have 0 is less than or equal to -1. Is that true or false? Well, 0 technically isn't less than or equal to -1, so that's false. And what that means is this point right here would not be in the shaded region, therefore it's everything on the other side. And guess what? That's where we already shaded. All right, let's try the next one. We have 3x plus y is less than or equal to 2. Wow, I need to get some different inequalities here, don't I? We'll make sure the bottom ones are greater then, just to have something different. Now in this problem, what we have to do first is make sure to get y by itself. 3x plus y is less than or equal to 2. This would be kind of in general form. All we need to do is subtract the 3x to get y by itself. So not too difficult. Y is less than or equal to -3x plus 2. Starting with our y-intercept at +2 with a slope of -3. This means we have to go downhill, so we're going to count down 1, 2, 3, 1 to the right, 1, 2, 3, 1 to the right. And then if I go in reverse, if I count up 3, I need to go 1 to the left. And again, check the type of boundary you have. Should be solid, so connect those dots edge to edge. Whoops, get that in there as best you can. And then shading below again. So now watch what happens this time. Go to your y-intercept. If you want to shade below, we're actually shading over here on this left-hand side for our solution. And that's an example of shading with a translated slope and y-intercept. What happens if we have just x or just y? The same thing that would happen in lesson 2.3. Just x means this is going to be a vertical inequality. So the line is going to be vertical. Go to -3 on the x-axis and put a dot. And I want to go up and down from that location. But because it's just greater than, this is going to be a dashed boundary all the way through. And then it's dealing with x and not y. So to determine where to shade, when our value is greater than -3 on the x-axis, that would be to that right-hand side. This means everything over on that right-hand side is going to be valid for our solution. All right, one more. 1/2 x, so of course we have to have a fraction, obviously. 1/2 x minus y is less than or equal to -3. First thing you want to do is isolate your variable. Let's move that 1/2 over by subtracting. All kinds of negatives here. -y is less than or equal to -1/2 x minus 3. Now to get y completely isolated, make sure to divide both sides by -1 and watch what happens. We get y by itself on the left, but then less than or equal to becomes greater than or equal to since we divided by a negative. -1/2 divided by -1 becomes +1/2 x, and then -3 divided by -1 becomes +3. All right, see if you can sketch that graph and shade the appropriate half plane. When you're done, press play and we'll move on. And there we have the shaded solution for y is greater than or equal to 1/2 x plus 3. Let's see what happens when we incorporate an absolute value inequality. This should be interesting. Graph the absolute value equation using your dotted or solid line. So we're going to pull a little bit in from 2.7 and then shade above or below based on the direction of the inequality. Let's take a look. Y is less than -2 times the absolute value of x plus 3 plus 1. Notice the inside is going to translate our kind of turning point, 3 to the left. So we're going to go left 3, that's an F, left 3, and then we're going to go up 1. So our turning point is at -3, +1. Sorry, my cat Diesel is sitting right next to me right now and he's very distracting. He's trying to help. All right, let's plot -3, 1. That's going to be our pivot point for our absolute value. Then using that -2 Remember, it's not slope, but from that pivot point in each direction, we're going to count down 2 and then go 1 in each direction. So I'm just going to start on this left-hand side. From that turning point, down 2, go 1 to the left, down 2, go 1 to the left. Notice I'm at the edge. So go back to your turning point, count down 2, go 1 to the right, down 2, 1 to the right, down 2, 1 to the right, and there's our edge. So we have the boundary points. Based on our inequality, this is going to be a dashed boundary. So go ahead and connect from that turning point on the left side and over on that right side. Try your best to make sure it's dashed, not solid. And then shade the direction. Less than should be below. Going to where that turning point is below is right in between. What that tells us is we're going to kind of fill the inside of those boundaries for that absolute value. And that's how you graph an absolute value inequality. We're going to save this application problem for class. So that is the lesson for 2.8.